Okay, for our next problem, I want to use the example, find the integral from 1 to 3 of ln x dx to make two separate points. Uh, First of all, before I even make those points, I just want to observe something. I know some of you are saying like, oh wait, ln x, I don't need any tricks for that. Everybody knows that the integral of ln x dx is just equal to 1 over x, but that's not true. If you're thinking that, you're going in the wrong direction. The it's the derivative of ln x that is 1 over x, not the antiderivative. So that's not going to work because this is false. For those of you who are watching this on mute, I just want to make it clear that that's a false statement. So let's evaluate this integral. So for one thing, remember that the reason we're finding antiderivatives at all is so that we can use the fundamental theorem of calculus. We're trying to evaluate a definite integral. This is the first example we're seeing today that involves an actual definite integral. Now, I know that when you watch the u substitution video, I advocated that for definite integrals you would simply keep the integral in the variable u, change the limits, and evaluate it. There is a way to do that, and you can see in your textbook they give you a formula for that. I actually find it's just in the case of integration by parts, which looks like u substitution, but it's not quite. I find that it is it's a little bit more intuitive to simply find the antiderivative, change it back to x, and then apply the limits of integration. So, so anyway, the 2 points that I want to make here are number one, that we can use integration by parts as an engine to be able to find a definite integral. The other is that this problem itself demonstrates kind of an interesting choice of u and dv. So, the question is, so we want to choose u and dv. So, how are we going to do that in accordance with the principle that we want dv to be something that we can find an antiderivative of? It turns out that in this case, the easiest way to do that is going to be to set dv equal to dx, and that's really the point that we want to make here, which is that sometimes dv equals dx is a good choice. So that means that u must be ln x. So here we have that's u, and that's going to be dv. It doesn't really look like we've gotten anywhere, except recall that it's finding the antiderivative of ln x that's difficult. Finding its derivative is easy. So what we've done essentially is turn the problem of finding the antiderivative of ln x into the problem of finding the derivative of ln x, as long as we're willing to do some extra work. So now let's write du is equal to dx over x, that's correct, and v is equal to x. So we can now say that the antiderivative of ln x dx, that's just u and dv, is equal to x ln x minus the antiderivative of x times dx over x. So this is uv, and this is the integral of v du. Now, fortunately, that last expression, x over x times dx, simplifies really nicely, so that's going to be x ln x minus the integral of dx, which is equal to x ln x minus x, and we can write this maybe a little bit more simply as x ln x minus 1. So that's the antiderivative of ln x. We'll just come over here and actually use that, and we can say that the integral of 1 to 3 ln x dx is just going to be equal to x ln x minus 1 going from 1 to 3, like that. So we just plug them in. We just plug in the values 3 and 1, and we get 3 ln 3 minus 1 minus 1 times ln 1 minus 1. And by the way, that ln 1, it's the ln natural log of 1, and then that result minus 1. It's not the natural log of 1 minus 1, which doesn't exist because you can't take the natural log of 0. So this is going to be 3 ln 3 minus 3 minus natural log of 1 is 0, and then minus negative 1 is plus 1. So this comes out to 3 ln 3 minus 2.